Let's look at some other examples of simplifying difference quotients. Let me start with maybe the following one here. Let's say that f of x is equal to, we'll say, 2x squared minus 3x plus 1. And I want to find the difference quotient here. So the idea for simplifying these is you want to be able to simplify it so there's no longer an h in the denominator when you're done. And so that way, well, I shouldn't say no longer an h in the denominator, but you want to simplify it so that putting 0 in for h does not give you a 0 in the denominator. Okay? And so that way you can substitute it in and find out what the value would be. Okay? So here the difference quotient, remember, is f of x plus h minus f of x all over h. And so the idea here is I have to put in x plus h in for x on both of these. Right? So I have 2x plus h squared minus 3x plus h plus 1. So that's putting in x plus h. Then I just put in x. And so in parentheses, I get 2x squared minus 3x plus 1. And then all of this over h. So we want to simplify this. Hopefully we can simplify this all out that the h, I can take care of that h in the denominator. Okay? So here I'm going to FOIL this out and distribute the -3, distribute the negative sign there. And when I do that, I get x squared plus 2xh plus h squared, and then minus 3x minus 3h, and then I got plus 1, and then distribute the negative sign, negative 2x squared plus 3x minus 1, and all of this over h. Okay, now I can distribute the 2, so then I get 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 1 minus 2x squared plus 3x minus 1 all over h. Notice here that each time I say that this is equal to this and this is equal to this, they really are equal. Okay, I'm making the statements equal to one another, so at the end I know that what I end up with is equal to the difference quotient. Okay, so don't be lazy and just kind of do a little bit here, there, and scramble it around the page. Write an unbroken chain of equalities, and that's going to be the thing that helps you most from making a lot of the dumb mistakes that you could make. So this one cancels out with this one cancels out with that one, and then this one cancels out with this one. So what I am left with is 4xh plus 2h squared minus 3h all over h. Okay, and then I could factor out an h and cancel it out, and I'm left with 4x plus 2h minus 3. Okay, and this is the value of the difference quotient. Then if I wanted to find the instantaneous rate of change at any value of x, I could just plug it in to here. Oh wait, the actual value after h goes to 0, right? Then this term goes to 0 and I'm left with 4x minus 3. So this is actually the final value after you take the limit. Okay? And again, when you simplify it down to here, now you can let h go to 0 because you don't get a 0 in a denominator. So, and then you can put in, if you wherever you want to find the instantaneous rate of change for this function, you can put x in to this and get it. Okay? So let's look at a couple other ones. Let me just say, if you have any other polynomial, higher degree like cubed, fourth degree, it would work the same way. You would just have to take x plus h times x plus h times x plus h, and you would get a cubic there. And you would have to, expand everything out, and then when you cancel all the terms on top, you will be left with terms that contain, all of the terms will contain at least one h, so that you can factor it out and cancel out the h on bottom, and then you'll have something that you could take the limit as h goes to 0. So that would work for any polynomial, though the work gets very, very complicated as the degree increases. So let me show you two other very common difference quotients, okay, that come up. And so one would be something like f of x is equal to, we'll say, I'll just make it simple, the square root of x. Okay, so then the difference quotient here, okay, it's going to be f of x plus h minus f of x all over h. Okay, well, when I plug in x plus h here, I get square root of x plus h minus, this is just the square root of x all over h. So this is fairly simple, and in fact it's too simple, isn't it? There's nothing I can combine or simplify or cancel out. Okay, so it doesn't seem like there's anything you can do, but there is a trick here that's going to work when you have square roots here. It's a very common technique, and we're going to use it a lot in the next section when we take limits. And what that is I'm going to multiply the top and bottom by the same thing, except I'm going to change, it'll be this numerator, but I'm going to change the negative sign to a positive sign. Okay, so this would be x plus h plus the square root of x, and then I'll multiply the bottom by the same thing. And so the point here is if you multiply the top and bottom by the same thing, you're multiplying by 1. That doesn't change the value, right? And then what you actually have here is an expression that's like this: a plus b times a minus b. And when you FOIL this, the two middle terms cancel out, and you're left with a squared minus b squared. This is the difference of two squares. So when I multiply these together, it's going to be the x plus h quantity squared minus the square root of x quantity squared. Okay, that'll be the top. The bottom will be h times the square root of x plus h plus the square root of x. That's going to be what the bottom, I'm taking h times that. Got to make sure to have the parentheses there. Okay, well this is nice because this then becomes x plus h, and this will become minus x, and all of this will be over h square root of x plus h plus square root of x. Okay, well these are going to cancel out, leaving me with just an h on the top. And then we got h times square root of x plus h plus square root of x. Okay, well this h then cancels out here, and I have a 1 on the top, and then on the bottom I have this. And the neat thing about this, I do have an h in the denominator, but when I let this h go to 0, there's no problem. Okay, I can let the h go to 0, because this will just go to the square root of x, right? And it'll look like this. And you could rewrite that as 1 over 2 times the square root of x. So this is the difference quotient for that, the simplified difference quotient. Okay? And the technique here is multiplying the top and bottom. We can call this the conjugate of this. Okay? And when you do, here, the square roots cancel out and you're left with this. But then you're also left with all this as a factor on the bottom, but we can cancel out the h because now the x's cancel out, and you're left with something that you could let h go to 0. Okay, so that's a important technique there, multiplying the top and bottom by the conjugate. You probably wouldn't have thought of that on your own right away, but once you see it as a technique, you can try it out in a lot of different places, and you will find that it's pretty helpful. Okay, now let me give you one more. So if you have something like this, f of x is equal to 1 over x. Okay, so I want to find the difference quotient for this. Okay, so this is going to be f of x plus h minus f of x all over h. Well, now I'm plugging in x plus h into here, and I get 1 over x plus h, and then this will be just 1 over x, and all of that will be over h. So again, pretty simple. I can combine these over common denominators, so I can keep simplifying by combining those over common denominators. So 1 times x is x, and then 1 times x plus h. So subtract the product of those, I just get x plus h like that. And then it'll be x plus h times x. And then all of this is over h. Okay. And so this is on top. So now if I distribute that negative sign on top here, I get negative x minus h all over x plus h times x all over h. Would look like that. And now the two x's cancel out, and I have negative h over x plus h times x. And all of this is over h. Okay, and so now I can think of this as being h over 1. I can invert and multiply. Times 1 over h. And then these cancel out, and you're left with negative 1 over this. This will just be a 1, and that's a 1. So this is just x plus h times x. And the point now is, okay, there's still an h in the denominator, but you can let the h go to 0 here. That's not a problem. And so we can let h go to 0 because this will just go to x. So we got negative 1, and then we'll have an x here, and then this will also be an x. And so this whole thing becomes negative 1 over x squared. And so this would be the difference quotient for 1 over x. Okay? So these are techniques. So for this one, you're just combining over a common denominator, simplifying. In each of these cases, you're getting the expression to a point where when you put in 0 for h, you no longer have the problem of getting a 0 in the denominator. So you can do that final step, and you get an expression for the instantaneous rate of change, and then I could just plug in values for x, and this will give me the instantaneous rate of change at that particular value. So notice again, when I do this, every statement is equal to the next statement right down the line, so that I know that the first statement and the last statement are equal. So that is the difference quotient. So even if it takes some extra work, like distributing, you know, I'm not going to do a little here and spread work out with kind of pieces here and there where it's all jumbled up. I'm going to make an unbroken chain of equalities that is easy to follow right down to the very end. So, okay, so hopefully those help you. You now have kind of the techniques that you would use to find difference quotients for polynomials, a square root function, and an inverse, a 1 over x function.